Yeah, I don't mind. I'll let you know.
This computer's having a hard life. Right, anyway, while it thinks about its own memory problems, last lecture we had a look at linear power supplies for the first time, and I went on a bit about the differences between single phase and three phase, and then between half wave rectifier and full wave rectifier. We'll catch up in a bit. And then we went on about a model of the ripple in the half wave and the full wave, which is triangular. And we said that if we're cunning and we integrate the charge under the ripply bit, Q equals IT, I CD, WT, and so on and so forth, plug them all in together, you can work out how much ripple you're going to get for a certain load current and a certain size of capacitor. Or you can decide on your capacitor size given some load requirements. And that would make a pretty good exam question if I was the sort of person who had to set an exam, which I am. And then we went on for a bit about all the different types of, well not all, but some of the different types of full wave and bridge rectifiers. And I said importantly that in the full wave, the capacitors are replenished every half cycle, and in the half wave, the capacitors are replenished every cycle. So that's 50 Hertz for half wave in the UK system and 100 Hertz for the full wave in the UK system. Harry? Sort this bloody computer out, will you? Addo gets really sad the first time you open it. So I'm not going to sit in here. Just close it up and redo it again. Right, in the meantime, my notes are small, aren't they? So, briefly this lecture I want to talk about three-phase rectifiers, not because it's examinable, because it isn't, and I don't think I said that it's not, but I have said it earlier, because at some point you'll have to do a bit of machine stuff, even if you really don't like power. There's quite a lot of machines done in terms of research at Sheffield. If you go into my web browser, it's in the download report. So you'll get taught quite a lot of machine type stuff, and a lot of machines are three-phase. And there'll be some electrical power systems modules later on that'll deal with it as well. So if you've seen it here first, it won't be completely new then. Having done the three-phase stuff briefly, I'll give you a nice summary slide of linear power supplies, which will be the one that sort of prints itself onto your memory, hopefully. And then I'm going to spend the rest of the lecture talking about Zener diodes and regulation, as opposed to the production of DC, which is not necessarily a constant value. I've been banging on about how DC just has to be more than 0 or less than 0 and never go into the other. So you can never have above and below 0, you can only have above or below, and that's DC. It doesn't matter if it's varying a lot. That means there'll be the DC and some AC. The question of regulation and stabilization is the case of making a constant value. In fact, stabilization is making the output invariant of the input conditions. A while ago I had a slide which showed the full range of permissible voltages in the UK system, and it's something like 220 something up to about 250 something. $259 maybe. Anyway, stabilization is making your output indifferent to whatever the supply line's up to. Regulation is making sure your output doesn't change based on what load you put on. So if I had some tiny little bench power supply and I put 0.1 ohms on it, its voltage would probably collapse because it couldn't supply that current. If on the other hand I had an enormous three-phase system the size of a telephone box or something, it might be able to drive that load, no problem. The question of making the load invariant is not always possible. There are certain limitations, but some circuits we can use to make the load more or less make the power supply unaffected by the load. How we going there? No? Bloody slow there. Right. It should be downloaded. If it's not on upload, the Dropbox again. I'll do it now. Hang on. Brief intermission. Lots of this to try. Right, so if you're at the back, you're screwed. There's not enough in the packet. I'll teach you. Good one. Right. So when you fill out your feedback forms, make sure you say the computer in this theatre needs changing, because if I say it, no one will listen. But if you all write it down, it will get done. Nearly. Right then, so three-phase rectifiers. I said last time that most power systems that handle more than a couple of kilowatts in case you haven't got a point of reference, if you've got a fan heater or an oil-filled heater, because your landlord's tight and your room's freezing and there's frost on the inside of the windows, whereas this now you all live in Opal and everything's rosy. Just a quick show of hands, who's in Opal or Victoria Hall or whatever, any of those? Well, not many. Actually, I wouldn't like them to make too much money. So who's up at the edge? Have you seen any of the other members of U2? Right, so a few kilowatts is a fan heater that you can plug in 30 amp socket. A little bit more than that is a kettle. The kettle's going to be about 3 kilowatts-ish, unless it's one of those really small ones, in which case it'll be a bit less. So anything more than that's usually three-phase. And a three-phase power system has 3 live conductors instead of a single live and a neutral. It's got 3 lives, and usually it's got a neutral as well, depends how it's wired up. So the 3 live conductors carry power at the same frequency, but are displaced in phase by 120 degrees. On the next slide, there's a little picture that shows that, and there's 3 sine waves that are all shifted by 1/3 of a cycle, which is 120 degrees. And the main advantage of three-phase power is that it's continuously available. That's to say, unlike the single phase, where there are points where the voltage crosses 0, if you look at all the phases aggregated together, there is never a point where there is no voltage. And the phase currents tend to cancel each other out. That's to say, when one branch of the three-phase network is conducting a large current, the other two will be conducting less current, not necessarily zero, although in certain situations it could be. And these currents will tend to balance each other. So the way a street is usually wired up is house number 1 will be on grey, and house number 2 will be on brown, and house number 3 will be on the other new colour, which I can't remember what it is, black. And then house number 4 will be back on grey again. And the logic is that, generally speaking, the load will be the same in each house. So if it's evening, people come home broadly at the same time. Let's assume that nobody works night shift in this. And the load will go up because they come home, they want to cook dinner and watch the telly and do whatever else they do in their free time. So collectively, all the houses will take more, and at night, they'll all take less. So overall, there's balance across the phases. And the same goes for a machine. If you've got a machine and you run it on three-phase, you would expect the three phases to take broadly the same power into the machine. So if all the phase conductors carry the same current, more or less, they can all be about the same size. And the power transfer into a linear balance load is constant. So that's to say, if you were to drive a resistor of all three phases, as I have in that diagram there. So this is three phases and three four-wave rectifiers composed of two diodes. So this is the simplest of the four-wave rectifiers, and it's just copy-pasted 3 times. And I've said they're 3 different phases. But unless I'd said that, it isn't necessarily true. The diagram's quite generic. And they all run together into RL. So this is the simplest possible case. Three-phase systems are quite useful for electrical machines because in certain types of electrical machine, you'd like to have a magnetic field in the outer part of the machine which builds up and decays in such a way that it appears to be going round the machine. And what I mean by that is, if this is the outside of my machine, and there's an inner bit as well that rotates, and that's the middle, and we're looking down the axle of the machine, I could have, in the first instance, a magnetic field that was big field there, and then a small amount of time later, I'd prefer this to be a lesser field, and that to be a lesser field, and have my big field here, big field here. And if the machine worked in such a way that the magnetic field in the stationary parts would induce some current that would cause the middle bit to turn, if I had the field as if it was going that way and that way, I could drag the middle bit round, which is the principle of several kinds of machine. Having the phases spaced 120 degrees apart, if I call this one brown phase and the black phase is here and the grey phase is there, this phase is 120 degrees ahead of this phase, and this phase is 120 degrees behind that phase. So this one, then that one, then that one. So if I put brown down here again, without any effort at all, I've got currents which are in the order that I want to make it look like the magnetic field moves. So if you observe it over time, you'll say, well, the field is moving. The field's not really moving per se, it's building up and decaying. It's like in an airport, you've got those message boards and it looks like the words scroll. It's just that the lights come on and off at an appropriate time when your mind tricks you into thinking the words move. It's the same sort of thing here. The field doesn't really move, it builds up and decays. Anyway, that's not going to be on the exam, but it'd be good for you to know it. So DC output voltage from a three-phase system is approximately, and under very specific conditions that I've idealised, 0.955 times VS peak. That's the secondary voltage on the transformer, peak value. So if I said, what's the RMS value of a sine wave? You'll say, root 2 times peak value. Or peak value over root 2, or what's the peak value of a sine wave? Root 2 times RMS. For the three-phase system, the numbers are different. And the peak-to-peak ripple voltage is considerably smaller as well, which means that you can have a smaller smoothing capacitor for the same value of ripple. Now, smoothing capacitor is quite expensive, especially if you've got big currents involved. makes sense to keep the cost down. The reason you can have the smaller capacitor is the fundamental frequency of a ripple is 300 Hz for a 50 Hz system that's full wave rectified. So it would be 150 Hz for a three-phase system that was half wave rectified. In many situations, you don't need smoothing at all. If you had something like a bench saw or some such, you might find that it's just a machine plugged straight into the three-phase, and the machine drives a belt, and there is nothing more than windings and magnetic material. No fancy electronics at all. And actually, that turns out to be quite reliable. But where you do need smoothing, it's easier to achieve because the ripple voltage is smaller overall. And just to give you an idea about how expensive electrolytic capacitors can be, this Evox Riverite Chemet or Evox Riffer rather inconveniently for me about 8 months ago. So it will take you to a new website if you Google it, but it's all the same. 6,800 microfarads is quite small in terms of smoothing capacitors. Oftentimes you want several of these in parallel, especially if it's quite a high current application. If you were rectifying the mains directly, you'd want about 400 volts withholding voltage, and for one, you'll be paying about 85 quid. So if you need 6 or 7 or 8, it's probably going to be an even number. That's quite an investment. Could be the most expensive thing in your electrical system. So this is a good slide to keep in mind. This is all I'm going to say about three-phase now. We're back onto examinable material. Hint, hint. This is a slide which is probably too small to be of much use in the notes, but you can download it from the teaching resources. It's got the standard waveforms for the 3 types of single phase linear power supply that could come up on the exam. So it's worth remembering these diagrams if you can. So I'm going to spend most of the rest of this lecture talking about the stabilisation and regulation of DC power supplies. So we've seen the output from a rectifier and smoothing capacitor is often not a constant value. In fact, it can only really be a constant value if there's no load on it at all. And this isn't always desirable. Sometimes we'd like to be able to dial in 15 volts and know that we were getting it with negligible ripple. When negligible is obviously defined, and we'll say maybe 20 millivolts, maybe a bit less. Depends on your application. Sometimes microvolts is what you need. So the regular power supply with no regulation or stabilisation or anything like that isn't always good enough. On the other hand, it's quite good a lot of the time. I mean, if you were building, say, a guitar amplifier or something, you need a power supply, you won't need regulation. And there are some arguments to say that regulation would make things worse, but I don't want to get into that now. The effects of finite supply and transformer impedance make it difficult to decide what the DC component in the output waveform will be of the power supply, and it also makes it difficult to decide what the ripple will be. And as I said in the start of this lecture, the UK power supply can vary in voltage by a tolerance of 10%, which is 207 to 253. And we might say, well, if I've got a circuit which is supposed to output 15 volts, if I assume it's 230 coming in, what will happen if it's only 207 or 250? Will it go up and down? And if it will, is that going to be a problem? If you've got a power shower at home and you've tried turning on the lights downstairs, running upstairs, turning on the shower and running back down, if you've got somebody else downstairs, they'll tell you the lights go dim, because it really does make a difference. And the majority of that is the impedance of the wire in your building. The other problem with linear power supplies that haven't got any stabilisation or regulation particularly, is that the ripple frequency will always, or the the fact that there is ripple and that it has a certain set of frequencies in it means those frequencies will try and turn up in your circuits that you want to drive from this power supply. And if those circuits are sensitive to it, or at least you take no steps to make sure that they're not sensitive to it, you will find those frequencies turn up in your measurements or your audio output or whatever. And that may not be acceptable, although a lot of the time it may be acceptable. It depends on the circumstances. So we might like to try and mitigate the variation in output voltage due to the variation in input voltage, which is stabilisation, which is defined up there. And we might like to try and mitigate the change in output voltage due to the change in load conditions, which is regulation, which is also up there. And we can achieve this with a little circuit called a regulator. And there are two types, series and shunt. And these types can be further subdivided based on their principal operation, but for the moment we will only consider shunt regulators, and we will only consider one shunt regulator, which is the Xenodiode-based shunt regulator. In later modules, I'm pretty sure 340's been rebadged as something else now, but you can go and find it by clicking on the old modules link in the sidebar in the teaching resources. So if you look in whatever 340 now is, or in the course books for 118, which I said in lecture 1, was Horowitz and Hill and Sedra and Smith and Millman and Grohl, you can get a good survey of the various linear regulators that exist. And you could look into some switching regulators as well. But we're not going to talk about any of that here. So in both the series and shunt linear regulators, the lowest value of unregulated DC input voltage must be higher than the greatest value of output voltage that we require. So this circuit is incapable of taking 15 volts and giving you 18 out. Although you know of a circuit that could do that, I hope, because we lectured it a couple of weeks ago. Of course, that would have to be AC. So the input voltage always has to be greater than the output voltage by a defined margin. And that margin depends on the design of the regulator and depends on the design of the regulator. Before electrolytic capacitors were widely available in high capacitances in a small package at a reasonable price, although still the price isn't that reasonable. We had different ways of solving the problem of how to make a power supply, and oftentimes the smoothing would have been done with a big wound inductor. And if you're interested in that sort of thing, you can have a look at the books on the bottom of this slide. I can't guarantee they'll be in the library, because I don't think the library is sufficiently old. But you should be able to find electronic copies of them online if you're careful. So the operation of a series regulator is that it restricts the flow of current from the input to the output in such a way as to maintain a constant output voltage across the load. And the operation of a shunt regulator is that it restricts or increases its own current demand in such a way as to maintain a constant voltage across itself by dropping a varying voltage across a source resistance, RS, and since the regulator is in parallel with that load, the load voltage is regulated as well. So if I said, how does it work? That would be the sort of words I was looking for. So, to construct a shunt regulator, we need a device or component that can draw a varying current while dropping as nearly as possible a constant voltage. Essentially, we need a current sink. And we've already looked at something that will do this. It's a Xenodiode. And it is a variable current sink in the sense that once you've broken it down, its voltage doesn't change very much, but its current can change over a remarkably wide range. And I've talked about Zener diodes, how they're constructed quite a bit before, so I'm going to get through this at a bit of a pace. It's a PN junction diode where both the N and P regions are doped very highly, and the forward bias characteristics are normal to are similar to a normal diode, like a 1N4148 or 1N914, something like that. But the reverse bias characteristics are engineered so that the diode breaks down at a specified voltage. And the breakdown behavior is achieved by making sure your doping and your region widths are just right, so that you'll reach the breakdown field at a particular value of reverse bias. And that's the way that the majority of them work. So 6 volts and above, you need to break down the diode in the same way that lightning breaks down the air between the cloud and the ground, or between the ground and the cloud. In the case of less than 4 volts, the electrons and holes that are moving in the semiconductor are in such, they're moving with such momentum that there is some doubt as to where they are. And they can go from being on one side of the diode to being on the other without ever having been observed to pass through the diode, which is called quantum mechanical tunneling. And if you want to, you can read about it in Streetman. But for the moment, we'll say all Zener diodes are basically the same from a circuit point of view. How they work inside differs depending on their voltage they break down at. So there is a breakdown characteristic for a Zener diode, and the bit we're interested in is on the left. Specifically, we're interested in the change in current for the change in voltage. And if you look at the I by dV there, we've got quite a large change in current for quite a small change in voltage. And this is ideal for making our shunt regulator. We can actually say that that line represents a resistance as well, because Ohm's law says I upon V is conductance, and conductance is 1 over resistance. So we can call that line 1 over resistance. And that will come back, we'll come back to this and it'll be quite useful later when we need to know what will happen to our regulator. We'll need to know how good it's going to be at doing its job, which is stopping the changes in the output voltage. We'll be able to come to some conclusions about how good it's going to be, and the slope of this line will be significant. So under normal operation in a shunt regulator, the dynamic resistance will vary. So we'll move up and down that line in order to conduct just enough current through the device, through the diode, so that the voltage across the load is held constant. Oh, I talked about impact ionization before. Anybody really want to hear it again? Ah, thought not. Good. Oh, there's some more. Tell you what, if you're looking for a good diagram that tells you everything you ever need to know about how a PN diode works, that would be it. But if there's time at the end, I'll come back to it. So, of course, that sort of thing will turn up in the other half of this course, but for now, let's not worry. The Zener diode is normally used in reverse bias, and it will be assumed from now on that the cathode will be positive with respect to the anode. So there is no plus and minus, just anode and cathode. Because if I said plus and minus now, it would be backwards to what we said about plus and minus before when we were doing conduction state problems. So if anybody ever comes up to me and says, which one's the plus, I may briefly take leave of my senses and beat you to death. Anode and cathode, always, forever. So once the diode has been broken down, we put on a voltage across its cathode and anode where the cathode voltage is greater, which is sufficient to break it down, more than what the manufacturer says is necessary. There will be a small increase in voltage thereafter, and that will lead to a small increase in reverse current, and the relationship between those two will be 1 over the slope of that line. So the ratio of the change in voltage and the change in current, I would call the dynamic resistance, or the small signal resistance. And after Christmas, or actually it's not just after Christmas, it's in February now. Do you have any exams? Okay. Other years have some exams, but when we resume lecturing at the start of the second semester, we will spend an awful lot of time talking about the differences between large signals and small signals and how that comes to be useful in transistor circuits when we talk about amplifiers and so on. So I want to get in early with it while we're doing just a diode, because a transistor's got one more leg, and that tends to make it quite confusing for some people. So we will come back to small signals. If you don't like them by the end of this lecture, it doesn't matter. They will come back again and again. So the small signal resistance is variable, and it depends on the biasing conditions. That's to say, if I have my Zener diode at, say it was 15 volt Zener diode, so it's going to break down to 15, I've got it at 15, it's conducting milliamp, it'll have a certain small signal resistance, which I could work out. And then if I had it at 20 volts, it would have another small signal resistance, which I could work out, and they'd be different. But you can't work it out by saying, oh, it's the current divided by the voltage. Not as in, I'll worry about the current with respect to 0, and then I'll worry about the voltage with respect to 0, and then I'll divide one by the other and use Ohm's law. That will not give you the small signal resistance, it will give you something else. We will come on to how you work it out in a bit. But this is what the regulator circuit looks like. Now the RL in this diagram is the same RL that we've had in all of the power supply circuits up to now. So actually, there's only two new components, and one of them is a resistor. And I hope you feel fond of resistors by now, or at the very least, they're not too frightening. So let's assume that VI is bigger than the Zener diode breakdown voltage. If you do that, then in the beginning, the only current that will flow is the current through R1, which also flows through RL. Now I'm going to say that R1 is much, much smaller than RL. So the voltage that's on the output nodes ought to be basically equal to VI. And I've just said that VI is considerably larger than the breakdown voltage of the Zener diode. So as soon as we put this voltage on, as soon as we switch on VI, the Zener diode should break down, because the conditions that arise as we turn it on are such that it ought to. That's to say the ratio of R1 and RL is just about right. Now just about right could be quite wide. Standard examples could be, depends a lot on your application, but anything from RS is a kilo ohm to RS is 3 or 4 ohms. RL will be in the region of 10 kilo ohms, maybe up to 100 kilo ohms. So in all circumstances, almost, RL will be much bigger than RS. So we'll assume that the IL is constant. That's the load current. So we want in our circuit the current that flows in the load resistor to always be the same value. And we will adjust VI and see what happens. So this is the case of stabilization. We're worried about what happens to our output voltage when our input voltage varies. So a slight reduction in VI, we'll call it delta VI, will cause a reduction in the voltage across R1 of delta VI, and hence a reduction in the output voltage. You might think that's true. If we assume there's no Zener diode, it's definitely true. But the falling input voltage causing the output voltage to fall slightly causes the Zener diode to conduct slightly less current, because its cathode to anode voltage has now dropped, and we will be moving up this line. So we were living somewhere in the slopey bit on the left, say in the middle, just next to where the delta is for delta I. If we were there before and we adjusted the cathode to anode voltage on the Zener diode across the Zener diode, slightly making it smaller, the current will have to drop a bit, and because we're stuck on the line, we cannot just wander off the line. We must have moved upwards slightly. So voltage has dropped a bit, and the current's dropped as well. And it just so happens that the current through the Xenodiode, which is what the y-axis was on that graph, will fall by just the right amount to stop V out changing. It's not by magic, it's a kind of feedback. And the reduction in the total current, which I'm calling IT, that's the current through the load and the current through the Xenodiode, due to the falling voltage drop across R1, is compensated by a similar reduction in IZ such that IL and therefore V out are unaffected. I expect that's thoroughly confusing. What I'm saying is, oh, come on, not this again. I think somebody puts joke chalk in the lecture theatres. Well, I can't be the only one because somebody else has done all their writing in yellow. Can you see that? Alright, cool. This is going to be my VI. This is going to be my RS. I must edit that out. This will be my RS. This will be my Xenodiode. And this will be my RL. And we'll have the Xenodiode characteristics over here. So we'll say that firstly we'll call that point 1. These both on the film. Nice. So we'll say this starts off at maybe 20 volts, and we'll say this breaks down at 15. So when we first turn this on, these two will share the 20 volts because they're just a potential divider, and we're assuming this is switched off. And if I was to say, for the sake of argument, this is 10 ohms, and this is maybe kilo ohm. We'd say, all right, well, this is going to be very, very nearly 20 volts because the ratio of those is 1%. So this will be 19.9 volts across there, more or less. In that case, it's more than 15, so we'll have quite a lot here. Diode breaks down, conducts some current. How much current will it conduct? Well, it depends on the value of RS and the slope of that graph. So I've got 20 here, I've got 15 here, so I must be able to say what the voltage there is. Who's got the biscuits? How far did they make it? All the way to the back. Any left? No biscuits left. Right, so this is for honour alone. What's the current in RS? 20 on one side, 15 on the other. How many volts across it? Oh, come on. 5. 5? Can you see it's 5? If you can't see it's 5, you're not doing your tutorial sheets. Right, so how much current then? Half an amp? 5 volts, 10 ohms? Half an amp? No. What's he talking about? How much current? Get a calculator out if you need to. But if you need to get a calculator out, then you're not doing enough practice. Come on, what is it? It's divided by 10, for God's sake. Half an amp. It's nearly 11 o'clock in the morning. So we got half an amp there. That's 5 volts. So our half an amp is going to get distributed between our 1 kilo ohm resistor and our Xenodiode. Now, the majority of it must go through the Zenodiode because a kiloohm at 15 volts will only take 15 milliamps. So almost all of this, 485 milliamps, must be going through the Zenodiode. And we can say, well, in that case, we'll be somewhere on this curve, which represents 485 milliamps, and this point will be, it's not going to be exactly 15, because there'll be a small variation in this region, and 15 will lie somewhere in it, but we'll call it 15 for the sake of argument. You can write 15.01 or whatever. So what then if this went up to 21 volts instead? Now 21's prime, so you're all screwed. 21 prime? No, 3 sevens. 21's not prime. Let's make it really hard. 23 is definitely prime. Right then, so now you've got 23 here. Now you've still got about 15 here. Now it will change a little bit because now there'll be 7 volts across there. 15, 8 volts. Yeah, 8 volts across there. So 8 volts across there, so we'll have 800 milliamps flowing. So 700 and not really sure how many is going to end up in here. It'll be, that'll be 0.8 amps. So we'll have 800 milliamps, we'll have 15 and a bit volts, but we don't know how many because we haven't looked at the curve. Because this curve will not be available to you. If you want it, you'll have to come up with a measurement system to measure it. We'll just say it's 15. So when we say it's 15, we'll be saying, oh, well, there's still 15 milliamps in here. So there's still 485 milliamps in the Zenodiode. That isn't going to be true because we will have moved slightly that way along the curve. And there will be slightly more current in the Zenodiode. And there'll be slightly less current in the resistor. And this won't really be 15. But when you're doing the working out, you say it's a 15 volt Zenodiode, I will always assume 15 volts. So what you're secretly saying is actually the curve doesn't look like this, it looks like that. Which is very similar to what we said about the conduction state problems in the diode. I said, well, there's 3 ways of looking at it. You've got a diode that switches on at 0 volts and conducts an infinite current without dropping any voltage, which is that L1. And then there's another one which has got 0.7 volts offset. Same situation. And I said, well, there's a third one, which used to be on the board there. A third one which was here like this, where we had 0.7 volts and then a slope line, and we could say, well, the slope line's got a resistance. Well, it's the same situation here, but when we're doing the working out, we use the simplest possible one of only over 15. If I wanted to use the curvy one, I could say, well, it'll be 15.03 and carry on in that fashion doing all the working out, and you probably want to get a calculator out to do it. So now it's 785 milliamps in the diode, 15 in the 1K resistor. The important thing is the 15 is still there, and that's what we want to achieve. A situation where the Zenodiode will conduct just the right current to keep this value at 15 or whatever we decide, irrespective of what happens over here, provided this never drops below about 15. Because if this was 10, this would not break down, and you have a potential divider of these two, so this would not be there. It would be open circuit, potential divider of that, and this would be about 9.9 something volts. And your circuit wouldn't be regulating. If this then went up from 10 to 11, you'd have 10.9 something volts there, and it'd just be potential divider. So this is broadly the design approach, but it's formalised in the notes. You work out or choose, based on your knowledge of the load, the maximum current that will flow. Then you choose a Zenodiode based on the required output voltage. So I've said BZX55C, which is pretty common silicon Zenodiode, and it breaks down at 25 volts. So if you wanted a 4.7 volt one, it would be BZX55C4D7 and so on. And you use the diode's manufacturer's data sheet to find the minimum current required for proper operation. I have abridged this slightly. You have to worry about how much this needs to keep going. So you can't say all the current will flow into the load. This needs a small amount. So it's the smallest value of I Zener that still yields the correct breakdown voltage. And then you consider the conditions that are most likely to cause the regulator to switch off, which is the minimum input voltage. So this will be, how small can this be and still keep this in its conducting state? That's reverse breakdown conducting. So VI minimum minus V out upon R1, where R1 has the same meaning as it does over there. Oh, sorry. No, it doesn't. This is R1, or RS. So you can say, well, I've got the maximum load current plus the minimum Zener current must equal the current that flows in that horizontally drawn resistor. If not, our circuit will not do what we expect. So yes, if the value of R1 is larger than the current given by equation 1, there will be insufficient current under the worst case of input voltage to satisfy the requirements of the load and the regulator, which is what I just said. Therefore, equation 1 represents the largest acceptable value of R1. Of course, you could have it smaller. So usually you jiggle this equation to give you the value of R1. If you make R1 smaller than its maximum possible value and keep the circuit working, all that will happen is R1 will dissipate more power. So you'll have to get a bigger power dissipation resistor. Obviously you'll waste that power because it's just heat warming up the room, or the box that it's in, or whatever. So you calculate the worst case power dissipation in R1. So if you wanted to do that, you'd say, well, maximum input voltage, maximum load current. Because the bigger this gets, the more voltage drops across here. This should stay fixed. So if I said, well, this can be 55, I'd have to say 55 minus 15, and then whatever my maximum current is going to be that I've already ascertained from whatever the question asks or whatever the design consideration is, I'd say either I squared R, V squared upon R, or I times R, and I'd get the maximum power dissipation. Obviously, if it was 55 on the input, and I said, well, the input could go down to 20, your situation with 20 would not represent a maximum power dissipation because the voltage across the resistor would be smaller. And we could then go on to calculate the ripple, but there's another lecture in here afterwards, I think. So, that's only 2 slides. We'll get on with it. To calculate the effect of the Zener diode voltage on the ripple, we need an equivalent circuit. And this is going back to the beginning of small signals. We will worry about how the circuit looks from the point of view of the ripple. So I will take the ripple, which obviously I keep in some sort of jam jar, and I'll go and unscrew the lid and put my hand on because it might try and escape. And once I've got some tweezers, I'll get the ripple out and I'll drop it on the circuit. And depending where I put it on the circuit, depends how the circuit looks. So you may think I'm crazy that I keep ripple in a jar, but it depends where you look as to what happens. Now we will do a bit more of this next time, but we have to know some model of what the Zener diode looks like from the point of view of the ripple. And we need to be able to draw some circuit which represents what the real circuit looks like as the ripple sees it. Now if the regulator has been well designed, the diode will be broken down in the reverse direction, and from the perspective of the ripple signal, which will exist on the output node, the diode can be thought of as its dynamic resistance, which is the slope of this line. So we will reduce the diode, never mind the breakdown voltage, none of that DC stuff, only AC conditions, and it's the slope of this line which is important. And this will be the inverse of that slope, sorry, at a particular point. Now, strictly speaking, the slope is curve. The slope is a curve, and the curve does not have a constant gradient. If we drew the tangent, say we were here, tangent could be across there, but if we're here, tangent would be across there. So we would end up with different values, or different inverse values, of dynamic resistance. And it turns out that the whole circuit can be reduced to a potential divider, because I really like potential dividers and they're dead simple. So we're saying RD is the inverse of the slope of this line at some particular current. So if we've decided from our calculations that the Zenodiode will conduct 485 milliamps, we will end up here, we will do this slope of this line, get its inverse, and that will be our value for RD. If it transpired through some other calculations under different conditions that we only conduct 15 milliamps in the Zenodiode, could be up here. And if we were, this would be the inverse of the slope of the line, and that would be our RD. And obviously this is V and this is I, this has a much higher resistance than that does. So we'll plug in R1 from which is RS on the other board, and the value of RD, and then we say, well, what's our ripple? Well, we know what our ripple is because we previously designed a linear power supply to bolt onto this, and we'd have come up with some ripple calculation from the prior lecture. That would be our value of ripple. We just plug in the numbers, and out drops a new value of ripple. So V out will also be a value for ripple, and V out, if we designed our circuit well, should be much less in terms of AC component than V in, because V in is the ripple that we started with, and we need to regulate our power supply in order to get rid of all that variation. Well, we'd like to know how much variation is still there. What have we failed to remove? And that's what V out will be. Right, we will come back to this next time because that was a bit rushed. On Wednesday, I'm planning a lecture of demonstrations of all the various circuits. Consequently, despite the fact that it's 9 o'clock in the morning, please turn up early.